Hi, this is Maggie from Design Code Debug Repeat. Welcome to the channel. Recently, in one of my classes, a student asked for tips for recognizing when a problem requires the use of mod, since most students never learned about the mod operation prior to our programming course and don't have much experience with it. I thought that was a great question, so today we're going to talk about some of the common problems that are solved with mod. Let's get right into it. Before we dive into programming, let's have a quick review of the mod operation. I'll put chapters in this video in case you're very comfortable with mod already and would like to skip to the examples. We write a mod operation as dividend %, which is the operator for mod in many languages, divisor. For example, I can write in the idle console 10 $3. 10 is the dividend and 3 is the divisor, and the operation is going to calculate how much is left of the 10 after we take as many whole 3's out as we can. As you can see from the illustration and the result when I press enter, we can find how many times 3 fits into 10, which is 3 times. 3 times 3 is 9, leaving us with a remainder of 1. I want to note that the % is the operator for mod in many languages, but the language you're using might use a different operator, such as %% in R, or the keyword mod in Pascal or Ada, or perhaps there is no operator or keyword, in which case mod is most likely a function in the language, as in MATLAB. To understand mod and gain an intuitive sense of its applications, I urge you to solve a number of mod problems by hand. Confirm them with your programming language or calculator of choice, and look at the patterns you find. Try solving problems in which the dividend is smaller than the divisor, like 4 mod 9, and make sense of the result. And solve problems with dividends that increase by 1 modded by the same divisor, such as 1 mod 3, 2 mod 3, 3 mod 3, 4 mod 3, 5 mod 3, etc. One pattern you will observe is that the answer to a dividend modded by a divisor will always be between 0 and the divisor minus 1. For example, if you mod by 2, no matter what number you have for the dividend, the result will always be either 0 or 1. If you mod by 5, it will always be 0, 1, 2, 3, or 4. If you mod by 10, it will always be a value between 0 and 9. 0 is always what's left over in a dividend if the divisor divides in evenly. Do some mods and get a sense of how those patterns unfold and why. It will help you understand why the examples we're about to look at use mod, and will help you recognize a problem that can be solved with mod in the future. So, when in problem solving do you need to know the remainder of an integer division? Probably the most straightforward case is when you want to know if a value is evenly divisible by another. So, for example, is a number evenly divisible by 2, answering, is it even or odd? If we divide 2 into an even number, the remainder is 0. If we divide 2 into an odd number, the remainder is 1. So code to check if a number is even or odd would look like if number mod 2 equals 0, print your number is even, else print your number is odd. I can run this example a couple of times to demonstrate. I'm going to use Python for my examples because I'd like to do some examples with PySimple-GUI and pygame, but the mod operation should be the same in any programming language, at least for positive number examples. Okay, so just one more example of wanting to know if a number is evenly divisible by another. Imagine your doctor has prescribed a medicine you need to take every 4 hours. You can use mod to determine whether the hour is evenly divisible by 4, and have your program alert you in some way that it's time to take your medicine. I have a PySimple-GUI program that displays a clock and will additionally display time to take your medicine if the hour is divisible by 4 and it's 0 minutes, 0 seconds past the hour. I've commented out that test, though, and put in a test of if seconds mod 4 is 0, so that you can see the message display every 4 seconds. Since I don't think we want to sit here for hours to watch the program execute. I'll run that. You could use this same sort of logic in a game if you want something to happen periodically. For example, you might want a gate to another location to open every 30 seconds and then close after 3 seconds. Or you might want your player character to lose 1 unit of energy for every 5 seconds the player is climbing or swimming. Or you might want to spawn more enemies every minute. You can mod a counter that you update every time through the game loop to determine when the period has ended. Now, another sort of problem that you can solve with mod is dividing a quantity into nested units. For example, there are 60 seconds in a minute, 60 minutes in an hour, and 24 hours in a day. There are 12 inches in a foot, and 5,280 feet in a mile. There are 10 millimeters in a centimeter and 100 centimeters in a meter. The smaller units make up larger units, and the larger units make up even larger units, but there always might be some of the smaller units left over. And leftovers means mod. Suppose you're given a value in the smallest unit, and you want to figure out what that value is starting with the largest unit. This program, unitsexample.py, solves that problem for the 3 examples I just gave. But it's easier to visualize how mod helps us solve this problem with an example with smaller units. So let's look at an example that takes a number of pennies and figures out the equivalent number of pennies, nickels, and dimes. If you are not familiar with US currency, there are 5 pennies in a nickel and 2 nickels in a dime. Suppose we have 37 pennies. If we divide that by the number of pennies in a nickel, 5, we will find out the equivalent number of nickels. 37 divided by 5 is 7. If we then mod 37 by 5, we'll find out what's left over. That's the number of pennies left over after we've taken as many whole nickels out as we can. So 37 pennies is 7 nickels and 2 pennies. Suppose we further want to find out how many dimes that could be. 7 nickels divided by 2 will tell us the number of dimes, 3. 7 nickels mod 2 will tell us how many nickels are left over after we've taken as many whole dimes out as we can, 1. So 37 pennies is equivalent to 3 dimes, 1 nickel, and 2 pennies. Another example of nested units is a number system. If we look at a number in base 10, say 4,259, if we mod that number by the number base 10, we will get the last digit, 9. If we then compute an integer division by 10, we get 425. There are 425 whole tens in 4,259. We can repeat the mod then to find the next digit, 5, and then repeat the integer division to essentially chop off that digit and get the 42. There are many applications for this process of extracting digits, such as in a checksum algorithm or converting a number to another number base. In fact, here's a checksum. And this program uses mod twice. The first application is in the number to digits function, which I just described. The function takes an integer and removes each digit using mod, adding the digit to a list. It then divides by 10 to remove that digit from the number and continues in a loop until the number is 0. It has no digits left. It then returns the list of digits so we can compute a checksum on them. A checksum is used to validate that data is valid or hasn't been tampered with. It is used in cybersecurity applications, but there are also some common applications that you probably experience on a daily basis, such as a book's ISBN, credit card numbers, and barcodes. A simple checksum algorithm adds together the digits of a number and then mods by some other value, such as 10 in this code example. If the result of the mod is the expected value, which is calculated in advance, then the number most likely hasn't been tampered with. If the mod results in the wrong remainder, then one or more of the digits was altered and the checksum fails. You can see in this example that the digits, which are stored in a list after the number is sent to the number to digits function, are added together on line 23 and modded by 10 on line 26. If that results in the expected checksum, in this example 5, then the checksum passed. But if the mod has any other remainder, then one of the numbers was changed, resulting in a sum that doesn't have the correct remainder when modded by 10. In practice, checksums are usually a little more involved than simply adding the digits together, but more sophisticated checksums are variations on this simple theme. If you're interested, look up the Loon algorithm or how ISBNs work, which are two examples that are easy to understand. Now, reflect on the pattern of mod results I mentioned earlier in the video. If we mod by 12, for example, we will get results of 0 through 11 repeating, starting with 1. 1 mod 12 is 1, 2 mod 12 is 2, etc. through 12 mod 12 is 0, 13 mod 12 is 1, 14 mod 12 is 2, etc. through 23 mod 12 is 11, and then it repeats, 24 mod 12 is 0, 25 mod 12 is 1, through 35 mod 12 is 11. Mod is useful for cycling through a set of numbers, given a constantly increasing count. Suppose we want to know what time 1500 hours military time is on a civilian 12-hour clock. The hours of a 12-hour clock repeat 12, 1, 2, 3, 4, etc. through 11, and then again 12, 1, 2, 3, 4, etc. through 11. We can mod our military hours divided by 100, 15, by 12 giving us 3. 1500 military time is 3 o'clock, 3 p.m. 0300 military time is also 3 o'clock, 3 a.m. This pattern of mod is also useful when you want to access an indexed data structure, such as a list or an array, and you want to wrap around to the beginning once you've reached the end. Didn't that pattern sound familiar? If we have a Python list of size 12, the indices are 0 through 11, exactly the values we get if we mod by 12. To get an index in range, you can mod any value by the length of the indexed structure, provided you're using a language that indexes beginning at 0. If your language indexes beginning at 1, you'll just add 1 to the mod value to index correctly. If you want to index through cyclically, use a counter. Let's look at an example from a game animating a sprite. This is one of the examples from the video about using masks to change appearance. The animation images are stored in a list, which is an indexed data structure. There are 6 sprite images, which, when you swap them out one after the other and move the sprite a little bit in the direction it's facing, sort of like a flipbook, result in what looks like walking. So our list has a length of 6, which means the valid indices into the list are 0 through 5. In the code, I'm checking on line 113 if the sprite is moving. And if it is, I set the index into the image list to the current image index plus 1. So if we're currently displaying image 0, we'd now be displaying image 1. And if we're displaying image 1, we'd now be displaying image 2, etc. But what if we're currently displaying image 5, the last image in the list? When we add 1, we get 6, which is out of bounds for our list and would result in an error. So we mod the sum by the number of images, len self.images, which is 6. For 1 through 5, the mod would be just the original number, but for 6, the mod brings us back to 0, and we start over through the images. One thing that's important to understand about mod for this to make sense is that if your dividend is smaller than your divisor, the answer to the mod is your dividend. So for example, 1 mod 6 is 1, 2 mod 6 is 2, 3 mod 6 is 3, etc. Why is that? Remember the definition of mod that I gave. Whatever is left over in the dividend after we've taken as many whole divisors out as we can. You can't take any 6s out of 1, 2, 3, 4, or 5. So the result of the mod will be what you started with. In other words, you can take 0 6s out. So you have the whole 1 left over, or the whole 2 left over, or the whole 3 left over, because you took nothing out. You took 0 times 6 out. And this cycling through a list is also how a Caesar cipher works. If we think of the letters of the alphabet as an indexed data structure, beginning with A at 0, once we reach Z, we've reached the 26th letter in our data structure. If we were cycling through our letters like our animated sprite list, we'd add 1 and mod by 26. Now, a Caesar cipher is a way of encrypting a message by shifting each letter a set amount. For example, shifting each letter 3 to the right, as in this image from Wikimedia Commons. But what do we do with the letters X, Y, and Z? If we shift them 3 to the right, we end up going past the end of the alphabet. what we do is wrap around, which we now know we can easily do with mod. So if our letter is X, letter number 23 in our example that begins with A at 0, we get 26. We mod by 26 and we get 0. X encoded is A. Similarly, Y at 24 gets 3 added to it, giving us 27. Modded by 26 gives us 1, which is B. And Z would be C. This program demonstrates a Caesar cipher. If I run it, you can see the plain text hello world is encoded to Kurzrogue and then decoded back to hello world. The encode function does the work of shifting one letter. It first checks if the character to be shifted is a letter. Now, the shifting code is slightly complicated by the fact that the letters don't begin at index 0. That's all the start variable is doing. It's allowing us to subtract out the characters before A. So we're beginning at A equals 0 and then adding it back in once we've shifted. So we're back within the range of letters in the Unicode table. So if you ignore the start code, you can see we're adding the shift and then modding by 26, exactly as in our example. So that's an overview of when we might use mod to solve a programming problem. To summarize, we'll use mod when we want to know if a number is evenly divisible by another. For example, to learn if a number is even or odd, or to learn if an interval has passed so we can add some enemies to our game or take our medicine, or to learn if a number was compromised when we're computing a checksum. We'll use mod to distribute nested units into their larger bins and find out how much is left over in the smaller bins, such as with time, money, numbers in a place value system, or units of measurement. And we'll use mod when we need a pattern of repeating numbers, such as when we're accessing elements in an indexed data structure or a conceptual structure of limited size, such as the alphabet. I hope you found this video interesting and that it will help you recognize mod in problems so you can implement an appropriate solution. The code examples I've shown you will be uploaded to my GitHub repository. There's a link in the description. As always, have fun and keep coding.